All right, for class 23, here's example 2. And I should explain this a little bit. When I was at the Coast Guard Academy, it was pretty, I don't know, I'd been there a couple of years, but one of the bosses came around and said, hey, we're looking for the end of year money that we have available, and what kind of things would you like for your class, to teach your class? And I was teaching dynamics. And he had passed around a catalog, and I ran across this Hovercraft, right? So I'll show you what the Hovercraft looks like. I'll see if I can bring this up here. Okay, so this Hovercraft here, this Pasco Hovercraft, this thing shows up. I don't want to chat with you. And so it looks like this right here, right? Where you have this cordless leaf blower sold separately, cordless air source. And you sit on this little disc, and there's actually a little, like, it's somewhere in there. There's a little level, a little circular level. It's got a little bubble in it, and if you distribute your weight just the right way, you will hover and you'll have frictionless motion. And I thought this was cool. And I'm like, every time they ask, "What do you want?" "I want a Hovercraft." Yeah, and so it was sort of an obsession of mine, and years went by, and every time I got asked the same question, I'd ask for a Hovercraft. And it wasn't until my last year at the Coast Guard Academy, they went and they bought me 2 of these Hovercraft, and just like I had always wanted, we took the cadets out in the hallway and actually went into the machine shop where there was some open space, and because it was a big machine shop, and we had the cadets, and we would put them on there, and we would thrust them at each other and watch them bounce off of one another. And then we also did the conservation of angular momentum on board, and it was just an amazing thing, and it was a dream come true. And then I left. So I still want me some Pasco Hovercraft. It's on my wish list. So that's why there's a Hovercraft thing here. So a student is on a spinning Hovercraft holding 4-kilogram dumbbells. I'm not even sure how much that is. I should look it up. 0.6 meters away from their body, traveling initially at 1 revolution per second. That's just easier to think. 1/1000. That's 1 revolution. The maximum inertia of the person in the platform is 0.4 kilogram meters squared. The mass moment of inertia of each dumbbell is 0.001 kilogram meters squared. All right, that's really small. All right, so we want to find the rotational speed if the cadet, see, I left him as a cadet. He was a student. I changed him to a student when I came here, but let's change him right here. I'll make him a student because we are not at the Coast Guard Academy anymore. Brings the dumbbells inwards to about, whoops, just jump back here. Well, we already did this one. Boom. Okay. Brings the dumbbells inward to 0.2 meters from the body. So we want to find what that rotational speed is. This is just like the figure skater thing. And you can try this yourself if you have a couple dumbbells sitting around in a desk chair. Try it out. You don't need a Hovercraft. But anyway, here I drew my models here. Here's before and then after. I didn't draw the impulse one because there is no external impulse. Everything is internal to this system. I'd also mention that the velocity of the dumbbell, here's a little kinematics, is equal to omega times r. R being the distance that the dumbbells are from the outside. So we start with the system momenta in the beginning, the system external impulses, and then the system momentum at the end. And because there are no external impulses, we have a conservation of angular momentum problem. And so coming through here, we have the what the person is, what the whole assembly is, the non-dumbbell parts of the thing is going to be IP times that initial angular velocity. We also are going to have the dumbbells themselves. They are spinning. You know, because it doesn't matter where you're spinning if you're an object everything's connected to each other. If one thing is spinning at a rate, that other thing is still spinning at a rate. It's not spinning about any particular axis. And then we also have the mass of the dumbbells, right? And the linear momentum right there. But that linear momentum is positioned at a distance from the center, right? And not only that, but that linear momentum can be expressed in terms of angular momentum. that linear velocity can be expressed in terms of angular velocity. I think I said that right this time. One more time. That linear velocity can be expressed in terms of angular velocity. And then we have the second state, where everything is pretty much the same, except that we have a different angular velocity going on here, or a different, the second stage. And we could put everything in terms of that angular velocity. And that's really cool, because now we can plug some numbers in there, and now we have this relationship before and after. And we do that, and you'll see that it's more than 4.5 times the speed. That's pretty remarkable, right? We moved from 0.6 meters outwards to 0.2 meters inwards, and you started to fly faster. Now, I asked the question, can this be done? All right, so can this be done with work and energy? And pause to think about that for a minute. We'll have this being the student is thinking that, right? So, can this be done with work and energy? That's what he's asking right now. And the answer is nope. Why not? Well, because of muscles. Yes, that's right. That muscle he might be in here, right? But there was chemical potential energy that was contained inside his or her body, and that turned into physical energy, right? And your muscles converted them. From the glue, from sugar in your bloodstream, you were able to power those muscles, or however the heck that works. And they show some ignorance, don't I? And we were able to put external energy into the system when the muscles pull the weights inward, right? And that right there makes it non-conservation of energy. And we don't know, we can't quantify exactly how much that would be. It would be a little difficult. We could try to start thinking about it. It could be a thought experiment, but it's an interesting and important thing to note. It's easy to fall for these application of the conservation of energy, or the conservation of angular momentum. Even you got to be careful that there's no external thing happening to it. We also have to make sure, when it's conservation of angular momentum, that there is a point about which that we can pull things and we can get rid of some forces, right? So these are all important stuff to keep in mind. But it's an interesting exercise to do, to do this little spinny thing, just like ice skaters, right? Figure skaters, they do. So just remember, if you wanted to buy me something, and donate something when you're a rich alumni, get me a bunch of Hovercraft. I could sure go for a Hovercraft. Thank you.